Hello, this is Professor Kuehn. Let's continue our discussion of Ptolemy's Almagest. We are on chapter 7, where Ptolemy argues that the Earth does not make any motion from one place to another. In other words, the Earth is sitting still. Here, once again, Ptolemy is in agreement with Aristotle's geocentric worldview. What is the evidence that he provides? Well, he says, if the Earth were moving around, the horizon, he says, would not bisect the celestial sphere. You might recognize this as being very similar to his argument in the previous chapter, chapter 6, where he argued that the Earth had any appreciable size compared to the celestial sphere, then the horizon would not bisect the zodiac. So remember, here is the celestial sphere with Polaris on the North Star at the top. And if the Earth was in fact moving around, let's draw a little line depicting the Earth moving around. If the Earth were moving around this axis, at some particular point, let's say when the Earth is over here, if you were standing on the Earth, one could draw a horizon line that is tangent to the Earth, and at that moment in time, you would not have half of the celestial sphere above and half of the celestial sphere below the Earth. Rather, you might only have a quarter of it above and 3/4 of it below. Since this is never the case, since we always see half of the celestial sphere, half the constellations above the horizon and half below the horizon, that implies that the Earth must remain near the center or at the center of the celestial sphere. Therefore, the Earth does not make any motion from one place to another. That's the first argument that he provides. The second argument that he provides is he says if the Earth were moving around, then falling rocks which seek the center of the world would not strike the Earth at right angles. What is he saying here? Well, let's draw another picture of this celestial sphere with the Polaris on the North Star, or at the north part. Here is the center of the celestial sphere. Let's suppose that the Earth were moving around, so at some point in time it was not at the center of the world, the center of the universe. If that were the case, and if you were to stand on the Earth and drop a rock, the rock which you drop, which is seeking to go toward the center of the world, would not hit the surface of the Earth at a right angle. It would hit it at a funny angle. Notice here he's using the same kind of argument that Aristotle had used. He's assuming that rocks, when dropped, move toward the center of the world. They're not attracted to the Earth itself, as modern gravitational theory or Newtonian gravitational theory would have it. Rather, he's adopting the Aristotelian physics that rocks seeks the center of the world. And he's using that assumption as a justification for his view that the Earth, in fact, must be and remain at the center of the world. Okay, let's look at his next argument. At the bottom of page 49, he says that those who think it a paradox that so heavy a thing as the Earth has neither been held up by something or moved seem to me to be mistaken. What is he talking about here? Well, there are people who argue that if one claims that the Earth is stationary, something must be holding it up. Remember, there were critics of Aristotle who also claimed this. But he says at the top of page 50, that's a mistaken approach. After all, he says, what do we mean by up and down? By up, we mean away from the center, and down meaning toward the center. So there really is no up or down apart from the up associated with away from the center and down associated with toward the center of the world. So you don't need to have this debate about what holds the Earth up. It's simply at the center of the universe. This again is on page 50, I think on the first full paragraph on this page. Now, on the bottom of page 50, he begins with, I think, his strongest argument, or perhaps he believes his strongest argument for why the Earth must be sitting still. And again, the idea here is common sense. We are standing here on the Earth, sitting here on the Earth, watching our computers or however you're watching this video, and you feel like you're sitting still, and so you are. That's the evidence that he provides. He says here that if the Earth were moving or falling in some way, then the things on Earth would be left behind as the Earth is moving through space. We don't see things being left behind as the Earth flies through space, and so that's evidence that the Earth is not moving. Now, he says that some would claim that the Earth moves and also the atmosphere and the inhabitants of the Earth are moving along with it, and that is why they do not feel the motion. But he argues, he provides a counter-argument. He says that the rotation of the Earth would if the Earth was moving, that would not be a natural motion, but a violent and unnatural motion. In fact, it would be the most violent or unnatural motion, even more violent and unnatural than the motion of the air surrounding it. And so what would happen is the air would be left behind, he argues, and there would be hurricane force winds blowing across the surface of the Earth and blow everything over. Now, you might or might not find these kinds of arguments convincing, but the central point he's trying to make is that if the Earth is either spinning around its axis or it's moving in some way, there should be some discernible effect here on the surface of the Earth. There should be something funny happening when we throw things up in the air, when we drop them, that should result from the motion, the spinning, or the rotation of the Earth. And since these kind of effects are not seen, it's evidence that the Earth is in fact sitting still. It's interesting to note that the most compelling evidence for the motion of the Earth, from doing experiments here on Earth, doesn't really come until the 1850s. So specifically in 1851, there's a man named Léon Foucault who developed what is now called Foucault's pendulum. This is something you may have seen at science museums. It's a pendulum hanging from the ceiling, and it swings back and forth. And over time, as it swings back and forth, the plane of the pendulum rotates around. And oftentimes they have a row of dominoes sitting around this pendulum, and it slowly knocks over these dominoes as the plane of oscillation or swinging of the pendulum rotates. That was not developed until the 1850s, and this is meant to demonstrate that the Earth is in fact rotating. Keep in mind that the 1850s, this is over 200 years after Galileo wrote his defense of the Copernican theory that the Earth is in motion. So this very compelling evidence that illustrates the motion of the Earth using experiments right here on Earth aren't done until 2 centuries after the Copernican or heliocentric theory is developed. And this is the point that Ptolemy is making in the 2nd century AD, is that we should be able to have some experiments that demonstrate the rotation or motion of the Earth here on Earth. And those are not available at the time of Ptolemy, and they're in fact not available until the 1850s. There's a nice, the situation is described nicely in a book called Setting Aside All Authority, Giovanni Battista Riccioli and the Science Against Copernicus in the Age of Galileo. This is written by Christopher Graney just in the past few years. It's a fabulous historical account of this debate. Okay, so that is Chapter 7 in A Student's Guide to the Great Physics Texts. Let's stop there, and next time I'll talk about Chapter 8.